Bioinformatics Micromodules, Suffix tree. In this module, we introduce the suffix tree index structure, which also makes use of suffixes to perform text search, but requires much less space than suffix trie. Recall that in order to index a sequence of length n using a suffix trie, the space required is order n squared in the worst case. To deal with this high space complexity, a first idea is to reduce the number of nodes by merging each node with its child if the node has only one child. In other words, if there is a linear non-branching path down the tree, we collapse all the nodes on the path into a single node. For our suffix trie shown here, after this merging step, the result is the tree on the right. We can see that the number of nodes in this new tree is much smaller. It has 16 nodes, while the original suffix trie has 58 nodes. Although this reduction from 58 nodes to 16 nodes in our example is great, in general, does this merging step reduce the space complexity? To answer this question, let's think about the maximum possible number of nodes remained after the merging step. This seems to be a number difficult to determine because the number of nodes at each level of the suffix tree varies from sequence to sequence. However, if we think carefully, after the merging step, the tree must have no more than 2n-1 nodes for a sequence of length n, and thus this number of nodes is linear with respect to the length of the sequence to index. This is true no matter which sequence is indexed. To see why, first, we need to notice that there are exactly n leaf nodes in the tree after the merging step. This is because in the original suffix trie, there were n leaf nodes due to the special $ symbol, and during the merging step, no two leaf nodes were merged together, since each of them could not be an ancestor of the other by the definition of being leaf nodes. How many internal nodes are there in the tree after the merging step? The answer is no more than n-1. We can understand this by considering the n leaf nodes as n disjoint components, and we want to use the internal nodes to ultimately join them to form one single connected component. By the definition of suffix tree, each internal node must have at least two children after the merging process, and therefore each internal node reduces the number of components not yet connected by at least one. As a result, with at most n-1 internal nodes, all n components would have been joined together. To conclude, there are n leaf nodes and at most n-1 internal nodes, and therefore the total number of nodes is at most 2n-1, which is order n. Although the number of nodes is now linear with respect to the length of the indexed sequence, storing the subsequences in the nodes is still a big problem, since their total length can be of order n squared. To tackle this problem, we use a second idea, which is to store only the starting and ending positions of each node label. For example, for the tree we obtained from our example shown here, if we store only the starting and ending positions, we get this new tree on the right. We will refer to this index structure as the suffix tree, which is essentially a compressed form of the suffix trie. What is the space complexity of the suffix tree? Since the number of nodes is order n, and for each node we need to store only two numbers, you may think that the space complexity is order n. This is correct if we assume each position number can be stored in constant space. However, in general, each position number should require all the log n bits to store, since it has a range between 1 and n. And therefore, if we take this into account, the space complexity of suffix tree should be order n log n. Now, let's see how we can use the suffix tree to perform text search. The procedure is similar to the one with suffix try, except that now we need to deal with the positions of characters instead of the characters themselves directly. Suppose we want to search for TATA. The first thing to check is whether there is a child of the root that corresponds to a subsequence starting with T. We can either check every node at this level one by one, or we can use exactly 5 slots to store the children of the root respectively for subsequences that start with $, A, C, G, and T, and check if the T slot is empty. Using either way, we should find this node highlighted in red that corresponds to a subsequence starting with T. Next, we should check the whole subsequence represented by this node, and in this case, it is S1.1, which is T. This whole subsequence matches the beginning of what we are searching for, and therefore, we can continue the search with the remaining of the query, which is ATA. To do that, we ask whether the current node has a child that corresponds to a subsequence starting with A. The answer is yes, and this node corresponds to the subsequence 2.2, which is A. Since it matches the beginning of what we are searching for, we continue the search of the remaining of the query, which is now TA. Just like before, we want to know whether the current node has a child that represents a subsequence starting with T. The answer is yes, and this node represents the subsequence as 3.11, which is TACA $. Its beginning matches what we are searching for, and we have exhausted all characters in the query after this match. Therefore, we conclude that TATA is contained in the indexed sequence. On the other hand, just like performing text search using a suffix try, if at any stage we cannot find the next character on our query, we conclude that the query does not have an exact match with the indexed sequence. In the case that the query can be found in the reference, how can we find out the exact occurrence positions? Let's use another example to explain. Suppose we are searching for A, and we have followed the previous procedure to draw the conclusion that it is contained in the indexed sequence after reaching the node highlighted in red. Now we see that the subtree rooted at this node contains 4 leaf nodes, all highlighted in green. Each of them represents a suffix that starts with A, and therefore there are 4 occurrences of A in the reference sequence in total. For the first leaf node, that represents positions 5 to 11. When we go down the tree from the root, before reaching this leaf node, we have to first go through the red node, which represents a subsequence with 1 character, namely as 2.2. Therefore, the actual suffix represented by this leaf node must start at 1 position before position 5, which is position 4. Therefore, we conclude that the 4th character of the index sequence contains 1 occurrence of the query. In the same way, for the second leaf node that represents position 10 to 11, the suffix should start at 1 position before position 10, which is position 9. For the third leaf node that represents positions 4 to 11, before reaching this node, we have to first pass through 2 nodes that represent S2.2 and S3.3 respectively. And therefore, the suffix represented by this leaf node should start at 2 positions before position 4, which is position 2. Finally, for the 4th leaf node, its suffix should start at 2 positions before position 8, which is position 6. To conclude, the 4 occurrences of A in the indexed sequence are at positions 4, 9, 2, and 6, respectively.